In the first part of this 2 micro lecture series, we defined an atomic number as a number of protons something has and said that all atoms of the same element have the same number of protons. This is true. We also said it was going to get more complicated when it came to neutrons. Also true, because not all atoms of the same element have to have the same number of neutrons. Specifically, isotopes are atoms of the same element with different numbers of neutrons. Carbon comes in at least 3 forms, at least 3 isotopes. The most common one by far is carbon-12. Then we also have carbon-13, which has 7 neutrons instead of 6, and carbon-14, which has 8 neutrons instead of 6. And isotopes can be either stable or unstable, and how stable and how unstable they are matter for nuclear power, nuclear chemistry, and a lot of the things we're going to cover, maybe, even if we even get there during this high school class. So atomic mass is something we're going to be looking at in terms of atomic mass units. So uranium here has 238.028. Okay, how many protons does it have? Okay, that's easy, 92. How many neutrons? Okay, that's easy, 238.028 minus 92. Wait a sec. It's going to be a decimal thing. It's not a whole number. See, atomic mass units are actually going to be defined for, as far as we're getting, as basically the number of protons plus the number of neutrons. So one atomic mass unit is going to be, say, 1 proton or 1 neutron. It's actually being taken as, 1/12 of the mass of a carbon-12 atom. That's the precise way of looking at atomic mass units. But we can basically look at atomic mass units for most of our course as equal to the mass number. That still doesn't help here because we have that 0.028. Most element masses are not going to be whole numbers. They're actually going to be different than a whole number. And as you see here, of course, as I mentioned earlier, the number of neutrons is definitely not equal to the number of protons here in this uranium-238. Carbon's atomic mass is 12.011. How we determine this is by weighing the individual isotopes and calculating how many isotopes of each type are going to be present. This is going to be the relative abundance. We'll get to that in the next slide. Carbon-12 is 98.9% of all carbon atoms are going to be the isotope carbon-12. There's also carbon-13, which is 1.1%. And that's going to be weighted as such, and carbon-14 is going to be less than 0.1%. So we're going to actually do a mathematical equation. This will be something we'll be doing in class, but also your book shows you how to do it to understand the relative abundance. Here's your little math equation. You notice we kind of left carbon-14 out of there because it's so vanishingly small. So how to determine the most abundant isotope? So you look at this and say, well, is argon-39 or argon-40 more common? You're like, oh, argon-40 is more common, obviously. Could you use the following equation, though, to figure out the relative abundance, where you look at the 39 and the 40? Well, yes, but actually no. You see, what happens is you're assuming there are only 2 isotopes, and as we saw with carbon, that's not going to be true. So that equation is not going to be that simple as to be able to do it in reverse. You actually have to know the relative abundance and how many different isotopes of each element exist. Here's your periodic table, and you can see all these masses. Now you know how to find anything on the periodic table given the number of protons, and how to calculate the atomic mass of anything if you are given the relative abundances of each isotopes. That's a fair amount of math, and you should definitely spend some time practicing with lesson check 4.3 and the available things at the end of the chapter in your chapter review and assessment.